Okay, this video is intended to go over the law of sines ambiguous case, but first let's do a little bit of review. The law of sines says that if you have a triangle with angles capital A, B, and C with sides opposite, little a, little b, little c, that these ratios have to be equal. That's kind of easy to prove, actually. If you drop a perpendicular from one of the vertices and call it H, and then use right triangle trigonometry, for example, to say the sine of A is H over C, the sine of C is H over A, set the H's equal to each other, you get the sine of A is to A is the sine of C is to C. Okay, and some textbooks use alpha, beta, and gamma for naming the angles instead of capital A, B, and C. And another comment to make is that these ratios, you can use the reciprocals of the ratios. And, if that makes it easier to solve the equation you end up with. All right, and then a little review here. When you're solving a triangle, you're basically given three pieces of information, and you're supposed to solve for the remaining pieces. So, for example, if you're given three sides, then you want to find three angles, and you can do that with the law of cosines, which is another video. And for side angle side, the length of the third side is predetermined, and so you can find the missing side by the law of cosines, and then eventually use the law of sines to find one of the acute angles, or one of the other angles, and then the triangle sum theorem, the angles have to add up to 180 to find the third angle. In the case of angle side angle, or angle angle side, which is whenever you have two angles, you can always find the third angle. So this is an example of angle side angle. The length, or the third side, is predetermined because we just extend these sides until they meet. We can find the third angle and then use the law of sines because we now know a side and the angle opposite. That's when you use the law of sines. Similarly for angle angle side. But the ambiguous case is where it's not guaranteed that you actually have a triangle. So this is how I like to set it up with the angle. This is the unknown side right here. This side right here is the fixed side, the side that you're given. And you're also given the side opposite the angle that's given. But we don't know if we're going to actually have triangles created with that given information. You can call this the hinge side, or the hinging side. Picture it swinging on a gate here. Does it actually reach the other side? And here's another picture of a triangle where we're given the angle, the side opposite, which I'm going to call the hinge side, and C is the fixed side. And how do we determine if there are 0, 1, or 2 triangles? That's the question. And we're going to do that by comparing the length of the hinge side with the length of the altitude and the length of a fixed side, of the fixed side. To show you what's happening, here is a triangle where this angle A is 30 degrees, the fixed side is 14, and right now this circle with the dashed circumference has a radius of 4.5. It does not reach the ray that forms the unknown side of this triangle. And as I increase the size of that radius, when it actually hits the opposite side, we actually have a triangle. And if I let it get a little bit, oh, and by the way, altitude is B sine of A. Since this is a 30-degree angle, the sine of 30 is a half. Half of b is 14, so this altitude is 7. If I make the hinge side a little bit bigger than the altitude, now two triangles are formed because this side A hits the opposite ray, the ray forming the unknown side, in two places. There's the second triangle. We say it's an obtuse triangle. There's the acute triangle. Okay, so that's what we're going to look at in these upcoming screenshots. So here we have a 30-degree angle. The fixed side is 14. The hinge side is 7. It's too short to reach the opposite side. How do we know that? Because we compare it with the altitude. And the altitude is 14 times the sine of 30, or 7. So we say there are zero triangles when the hinge side is not greater than the altitude. If the hinge side actually equals the altitude, then we've got a right triangle. And we can use right triangle trigonometry actually to solve the triangle. We don't have to use the law of sines. In this case, when A is greater than H, and I put 8 here, the swinging side, or the hinge side, is going to hit this opposite ray in two places, so two triangles are formed. One where this unknown angle, that's opposite the fixed side, is acute, and one where it is obtuse. Okay. If A equals this fixed side, you've got an isosceles triangle, and you actually don't need law of sines to solve it. You could use just right triangle trigonometry, but since it's isosceles, the base angles are congruent, and if we add those two base angles together and subtract from 180, we can find this angle. So 60 from 180 is 120. And then you could use right triangle trigonometry to find that distance. And since the altitude bisects the base of a isosceles triangle, this would also be the same distance. You add them together and you've got, we solved the triangle without using the law of sines. When A is greater than C, so when A is greater than 14, it looks like that side A, if you picture it hinging around, will hit this line in 2 points, but it only hits this ray that forms angle A in 1 point. So this triangle is not, angle A is not part of the original triangle, so this triangle doesn't count. But this one does, because A is 30 is part of that triangle. So there's only one triangle when A is greater than C. How do you do or sketch a diagram to do this ambiguous law of sines? Well, I'm not going to read through this whole thing, but I'll just talk about the first 4 here. Sketch the angle with the known side first, so you might label this as 30. Put the fixed side here. Picture a swinging hinge side here and calculate the altitude. And if A is greater than that altitude but less than the fixed side, you know you're going to have 2 triangles. Okay, and I do want to go back to Desmos here for a second and talk about what happens if the given angle is not acute. What happens if I go over here? Well, the only way you're going to get a triangle is if the hinge side is greater than the fixed side. That's what it looks like. So in most of the problems where you're dealing with ambiguous case, the given angle is acute. If it's equal to 90 or greater, then the hinge side has to be greater than the fixed side. Otherwise, you don't have a triangle. You either have 0 or 1 triangle. Okay. So let's go to board 10. So let's talk about the steps to solve triangle ABC, given that angle A is 30 degrees. Side opposite is 10. That's the hinge side. And C is the fixed side. Here I've drawn angle A, and I'm targeting this side as the fixed side, so I'll put C equals 14 there. I'll picture the side opposite as the hinge side. I don't know yet if it's going to actually reach the opposite side, but I'll label it as 10. Draw an altitude. How do you find the length of that altitude? It's the sine of this angle is h opposite over hypotenuse, h over 14. That's supposed to be a 14 there. So h equals 14 times the sine of 30. If you don't have a special angle here like 30, if you have 42, you have to use your calculator. But since A is greater than H, 10 is greater than 7, we know, and less than the fixed side, we know that side A is going to hit this ray at 2 different points, creating 2 different triangles. The big one, and then this one here, where angle C sub 2 is obtuse. So let's go to the next board and actually solve that triangle. How do you do it? Well, we're going to use the law of sines because we know an angle, 30, and the side opposite. We're going to start by solving for C because it's the acute angle that's opposite the fixed side. So it must be true that the sine of C is to 14, its opposite side, as the sine of 30 is to 10, its opposite side. So if we solve for the sine of C by multiplying both sides by 14, we get this. So C is the inverse sine of whatever this number is right here. And it turns out sine of 30 is a half, half of 14 is 7, 7 divided by 10 is 0.7. So we're looking for an angle that has a sine of 0.7, and there it is right there. So angle C in this triangle is 44, and usually we only go to the precision of the given information. So we'd probably say 44 degrees, excuse me, instead of 44.427. And now you can find the third angle. Once you know 2 angles, you can find the third angle by adding the 2 known angles and subtracting from 180. So we get 105, probably rounding up to 106. And all that remains to finish solving this triangle is to find this missing side. Once again, we revert to the law of sines. This time I'll put the side on top so that it's easy to solve for B. So B is to the sine of B, which we now know, 106 degrees, as 10 is to the sine of 30. I could also have said as 14 is to the sine of 44. So B equals 10 times the sine of 106 divided by the sine of 30. We get 19. Okay, so this triangle is solved, and there's the 3 pieces of information we need. Now, how do you solve for this triangle right here? And the key is that we have to find this angle first, which is an obtuse angle. You can see that I said C2 is 180 minus C, which was 44.427. Why can you do that? So let me go to board 12 and talk about that for a second. What's true on the unit circle is if you picture an angle theta in the first quadrant and then a corresponding reference angle of theta in the second quadrant, the sines of those angles are equivalent. They're the y-coordinate of a point on the unit circle. And this angle right here, the terminal side of this angle is 180, take away theta. And so the sine of 180 minus theta is always equal to the sine of theta. And this table kind of proves it right here. You can see these are all equal. Okay, so if we go back to board 11, how do we find this obtuse angle? We subtract the acute angle from 180, and that gives us the obtuse angle. Then we can find angle B sub 2 by adding them together, C2 and the 30, and subtracting from 180. And once we know B sub 2, we can use the law of sines again. B sub 2 is to the sine of big B sub 2 as 10 is to the sine of 30. And there it is. So this little B sub 2 right here is about 5. Okay, and now we've got 3 pieces of information for the second triangle. Okay, and some textbooks, instead of using subscripts here, they'll use C prime, B prime, and little b prime to talk about the obtuse triangle. Okay, so let's finish up with, we're not actually going to solve these triangles, but we're going to decide how many triangles there are. So we're given that we've got an angle A, a side opposite, and I'm sorry, we're going to find angle A. We're given angle B and side B, and another fixed side, so that's side, side, angle. So I'm going to draw this side. I'm going to draw something that looks like a 22-degree angle. I'm going to label the fixed side. This is angle B. I'm going to say that this is side A is 24. The side opposite B is little b, which is a 5. I don't know yet if it's going to hit the opposite side or not. I can see it's not greater than 24 though. So I'm going to drop and ask the question. I call this H. How do I find H? Well, the sine of 22 is H over 24. So H is 24 sine of 22. So let's see, H is, say that one more time, 24 times the sine of 22. 24 sine of 22, I am in degree mode, so H is 8.9. Really actually close to 9. But B is not going to hit this opposite side, so there are no triangles for number 24. Let's try 25 and end the video. Okay, so for number 25, we've got a B and a B, side opposite. I'll draw angle B with the size of 20. I'll label A as 13. B is 6. And I want to know, what is H? Well, H is 13 sine of 20. 13 sine of 20 is 4.4. Since 6 is greater than 4.4 but less than 13, we're going to have 2 triangles. And the first angle that we'll solve for is this one right here. This is angle A this time. So we'll say the sine of A is to 13 as the sine of B is to 6. And then we'll solve for the other triangle by finding this angle, which is the supplement of whatever we find for angle A. Call this A prime. Okay, there you go. I'll be using this video to answer questions about the ambiguous case for the law of sines in the video.